So I'll be talking about stealing machine learning models via prediction APIs. And this is joint work with colleagues from Cornell and UNC. So as a small introduction, let me talk about supervised machine learning, the way we'll deal with in this talk. So suppose you have a set of data where each sample is labeled with a particular class, and you're going to train a predictive model over this data, and when you query this model with a new input, you're going to get a prediction, so a class label, and in some cases maybe more granular information like a probability score for each class. And you can then use this model in some larger application or maybe publish it for others to use. And this publishing of machine learning models is actually something that many machine learning as a service platforms are starting to advertise. And in such a service, a user will upload, sort of outsource the training of a model over her data to a cloud service. And other users can then interact with this model essentially as a black box through some particular prediction API. And in some cases, this user will even pay a certain fee per query that he makes to the model owner. And there's essentially two conflicting goals at work here. So on the one hand, you want this prediction API to be as rich and as available as possible because, well, it should warrant the fact that someone is going to pay for it. But, well, if you're going to monetize this model, you should make sure that it's going to remain confidential. And in some cases, we'll talk about as well, you might want to ensure that the data on which this model was trained does not leak either, because it might be sensitive. These are just a few examples of popular machine learning as a service platforms. In this talk and in our paper, we focus mostly on Amazon and BigML. The latter is quite interesting in this context because they actually take this monetization of models, or of everything actually, to a higher level, and they allow users to sell data sets or trained models or prediction queries to other users in the system. So in this setting, we consider a new type of attack we call a model extraction attack. And in this attack, an adversary interacts with a model in the cloud through its prediction API, and then tries to reconstruct a local copy of that model. And we want this local copy to be very, very close to the target. And by close here, you can think of something like 99.9% agreement in classification between the two models. So they're basically identical for most practical tasks. A few applications of model extraction. Well, the simplest could be that once you have the model locally, well, you don't have to pay to use it anymore. So you sort of avoid this monetization if extracting the model is cheaper than what you would pay to use it for all the queries you want to make. And we'll also talk a bit about how you might use an extracted model as a stand-in for white box attacks over a model. And we'll see an example of this for privacy preserving attacks. Some parentheses dangling there. So if we take a step back and look at what we're actually trying to achieve with these attacks, one might ask, well, isn't this just machine learning? Because, I mean, we're interacting with a model and trying to replicate its input-output behavior. It's basically machine learning. There's two ways to look at it. Essentially, if the model, when you query it, only replies with a class label, so you give it an image and it tells you this is Bob, and that's it, then yeah, this is a setting that's usually called learning with membership queries, and it's been heavily studied in the machine learning and theory community. And there's been a few works that showed how you might learn or extract some specific model classes in this setting. But we find that this setting of machine learning as a service is actually quite different because these prediction APIs tend to return much more information than just a class label. And so we're in a bit of a different setting here than in traditional machine learning. Let me quickly go over some of our main results before I dive into the details. So we show efficient model extraction attacks against a number of popular model types that people might use. And we also show that in cases where the adversary might not know exactly what model type he's dealing with or what the features might be, you can still actually reverse engineer this process in a number of cases. And our attacks are extremely successful, so in a lot of cases we extract models that are virtually indistinguishable from the targets, and the attacks are very efficient. So with a few hundreds or thousands of queries to the target model, you can reconstruct this local copy. We demonstrate that these attacks work in practice on the services of Amazon and BigML. And let me just talk about one application of model extraction that I'll mention in this talk, which is in the context of model inversion attacks. And these were presented by Fredrikson and co-authors at CCS last year. Is a class of inference attacks on training data privacy. So here in the context of a facial recognition software, so you have the training data on the right, and then on the left an image that was reconstructed after an attack. And we show that if you first extract the model and then run this inversion attack in a sort of white box setting, you can actually get more performance, an attack that is more scalable. I'll come back to this later. So let me start with a simple example of a model extraction, sort of the simplest you could think of. And so here we consider a facial recognition task. So you have images of Alice and Bob, and you train a simple model that will try to distinguish these images. And here we consider a simple binary logistic regression model. And so this model just applies a logistic function, is this exponential inverse function of the inputs, where the parameters W and B are essentially chosen during the training phase so as to minimize the expected classification error. And these parameters, well, make up the model. And the output of this function can be interpreted as a probability of the input being either an image of Alice or Bob. You can then convert this into a class label. And this generalizes quite naturally to more than two classes with what's called a multinomial logistic regression. So how might one extract such a model? Well, as I said previously, you want to interact with this prediction API. You give it inputs X, you get this output F of X. And the crucial assumption here is that this API will actually give you this exact probability rather than just a class label. And this is essentially what all, I think, of the machine learning services we looked at actually do. And then, well, it's a simple matter of rearranging terms, and you get a linear equation in the unknown parameters that make up your model. So the takeaway, you do a bunch of random queries, essentially one per dimension or a number of parameters in your model, and you get a nice linear system of equation. Everyone knows how to solve these. And you extract a model that, up to maybe numerical approximations, is identical to the target. So we call this type of attack generically an equation-solving attack. We show that it can generalize to more complex model classes, such as sort of general neural networks, where the idea is essentially the same. So you take a bunch of random inputs, query your model, get the corresponding outputs, so these exact probability values from the model. And then again, you can set up an equation system in the unknown parameters of the model. Here we assume that the structure of the model is known. And, well, now the only difference compared with the previous case is that this equation system is nonlinear, so it's a bit more complex to solve, but there's very well-known techniques from the optimization techniques that allow you to solve these kind of systems, and this essentially corresponds to a kind of noiseless machine learning, where you're essentially using the exact same algorithms you would use to do machine learning, it's just that you have no noise in your system. The outputs that you get from this cloud service are, well, an exact mathematical function of the inputs. And so we demonstrate such attacks on a number of models we train, so multinomial regressions and some deeper neural networks. And in all cases, we find that we extract models that have extremely high agreement with the targets, and we only need a few hundreds or thousands of online queries, depending on the size of the model we're trying to extract. So now, having seen how these equation-solving attacks work sort of on paper, let's now turn to real attacks on an online system. So in our paper, we considered AWS for this. And here we'll need to sort of revisit some of the assumptions that we used in these equation solving attacks, basically about what kind of information is actually available to the adversary. So let's go through this pipeline in a bit more detail. So first, the user will upload his training data to Amazon, and then the cloud service will first apply a certain number of feature extractions. And these are essentially ways to select the dimensions of the inputs that are eventually fed into the model. And this process is automated. It's not fully documented by Amazon. But essentially what it ends up with is that the adversary doesn't know a priori exactly which features are actually used by the model. He doesn't even know exactly what type of model Amazon will train, because there's a number of different choices that Amazon might make. A small number, I mean, this is also not fully documented, but they say somewhat what they're going to train on your data. And so then you get access to this prediction API that the user can interact with. And when you send it a query, it's going to apply, the cloud's going to apply the same feature extraction to your query, then feed these features to the model, and send you back a class label as well as these exact confidence scores. One feature of Amazon service that is very useful actually in a number of our attacks is that they support partial inputs. So what this means is that you can send a query X where some of the dimensions are left unspecified. So you could think of, you send an image where some pixels don't exist, they have no value. And what the cloud will do is that it will set all the features that are derived from this input dimension to 0. And this is actually very useful, as I'll detail now. So this is what a real attack on AWS looks like. I'm not going to go into too many details about the feature extraction process. You can see more about this in our paper, but essentially Amazon will apply these two feature extractions, which are called quantile binning and one-hot encoding. And the essence is that, well, by actually abusing this ability to query partial inputs and get back confidence scores, we show that an adversary can fully reverse engineer which features will eventually be fed into the model. And so we're sort of back into the setting where we can assume that the adversary actually knows the set of features. For the choice of models, so here as well, there are some choices that are left unspecified and that the adversary doesn't necessarily know exactly what type of model he's dealing with. But here we find that a very crude brute force approach of just taking a set of plausible assumptions, trying all of them until one works, well, ends up working. And well, once you know how Amazon chooses the model, then you can apply the same ideas to every attack. So here are some results we got for two classical classification problems for handwritten digits and US Census data. And so with a few hundreds or thousands of queries, it takes a couple of minutes and small price that you have to pay for each query. We managed to reconstruct local models that are, well, have the exact same input-output behavior as the targets. So let me now talk a bit more about this one application of model inversion attacks that we looked at in the context of these model inversion attacks proposed by Fredrikson and his co-authors at CCS last year. So the setting we consider here is as follows. You have a facial recognition model that is trained over this AT&T faces data set. So you have images of 40 different individuals in a training set, and then you're going to train a logistic model over this, and well, we'll first extract this model using the techniques I've talked about previously. And then essentially we apply an inversion attack over this extracted model rather than applying this inversion attack directly over the black box cloud model the way it was done in this earlier work. And this attack will attempt to recover the image of one of the individuals in the training set. And then you can repeat this, well, 40 times if you want to recover an image for each of these individuals. And it's actually in this scaling of the attack that we find a nice improvement. So if you take the original attack as proposed by Fredrikson and his co-authors and sort of just apply it in a black box fashion directly over the trained model in the cloud, you need about 20,000 queries for one attack. It takes about 25 minutes with the network delay. And then if you want to reconstruct, well, every individual in the training set, well, you repeat this 40 times. And so you get quite a large number of queries and a long time for the attack. But you could also have a very high upfront cost by first running this extraction attack, which requires quite a lot of queries. It takes a long time because you're essentially building up this huge equation system and then solving it. But once you've done that, you have a white box model for which you can run any number of very cheap inversion attacks, actually. So doing these 40 attacks over a white box model is basically for free. And so we end up with an attack that is more efficient overall. Now I'm going to talk about a slightly different model class we looked at, which are decision trees. And here these equation solving attacks don't really apply because in a decision tree, the class labels and confidence scores aren't actually just derived from some mathematical function like a logistic function. Rather, you have this tree structure that is learned that partitions your input space into leaves. And in each leaf, you're going to just assign a class label and a confidence score, which is derived from the distribution of the training data for this particular leaf. And so there was this prior work, very nice prior work by Kushelevitz and Mansour that showed that if you only have access to class labels, you can actually reconstruct and learn Boolean trees in polynomial time. And this algorithm is, well, of theoretical interest. It has a fully impractical complexity. I doubt anyone has ever tried to implement it. So what we show is that if you make this extra assumption that you're going to get confidence values, you can get a much more efficient attack that's actually practical. So we show that these work very well on BigML's platform. Here to sort of quickly show how this works, we assume that every leaf of the tree gets assigned a different confidence value. So all the leaves had a slightly different training data distribution. In practice, we can sort of relax this assumption a little bit. The way the attack works sort of generically is that you take two inputs that differ in a single feature, and then you query them and check whether you get different outputs or whether you get different confidence values. And this acts as a distinguisher for the paths that these queries took in the tree. So if you get two different outputs, you know that somewhere the tree must have split on this feature that was different. And so then you can sort of iteratively apply this process and completely recover all the decisions that the tree has made. So how might one go about preventing model extraction? It's an interesting question. I mean, we propose a few possible techniques in our work. Here we'll look just at the simplest, which is just to say, well, if confidence values enable these strong attacks, well, let's just remove them and see what happens. And so, as I mentioned earlier, this sort of corresponds to this learning with membership queries setting. Where there was already some prior work that was quite interesting by Lauda Meek, for instance, that showed how you could extract linear classifiers. So these are classifiers that just apply some linear function on your inputs, and then, well, you select as one class or the other, depending on which side of the decision boundary you're going to fall on. And their attack here is quite simple. You just first query a few points until you get two of them that have a different class. Then you know the decision boundary must be somewhere here in between. So you do a binary search till you get 2 points that are extremely close to each other. You repeat the process. And then, well, you reconstruct this decision boundary up to some arbitrary precision. So what we look into is how this kind of approach could be extended to more complex nonlinear models. And here we look into a technique from machine learning that's called active learning. The idea here is quite simple. It's sort of an adaptive way of doing machine learning. So you query a number of points, you fit a model to these points, and then, well, you just query a bunch more points very close to your local decision boundary. This is implicitly where your model, intuitively, sorry, where your model is least certain about what's happening. And so we show that with this kind of iterative process, you can also get very successful extraction attacks, again, on these nonlinear regression models or neural networks, SVMs as well. Yeah, overall, these attacks work fine, but they're about 100 times less query efficient on average than if you just use equation solving when it applies, of course. So to conclude, we show that there's some kind of inherent tension in these machine learning as a service platforms between this desire to have these rich prediction APIs on the one hand, but also the need to ensure model and data confidentiality on the other. We showed that we can construct very efficient model extraction attacks for a number of popular model classes. We can also reverse engineer things that the adversary might not know exactly a priori, so the model type, the feature extractors that are used. And we show a few applications. So one I talked about here for model inversion attacks. There's one or two others in the paper. And our code is online, so if you're interested, you can take a look at that. And as I have, I think, 1 minute, exceptionally, I'd just like to conclude with a brief and shameless announcement to congratulate my older brother, Lucas, my slightly cooler brother, according to my Facebook feed, who, well, won an outstanding gold medal this morning at the Olympics with his rowing crew. So congrats to them on an amazing performance. Thank you.
We have time for questions. Since every one of you will have at least one question, please line up to the microphone.
Hi, Tavish Vadir from Georgetown. Very nice talk, and congratulations to your brother and to you as well. I just have a quick question. So have you thought of applying, so most of the attacks you talked about were for either classification tasks for machine learning.
I'm sorry, I didn't get it with the applause in
the attacks presented, you said, is for machine learning tasks that do classification and give you a score. Have you thought of applying these attacks to other machine learning tasks like speech recognition, where you can actually run the deep neural network and then try to do what like Apple, Siri, and Google now is doing on your own laptop?
So we didn't look into these. It would be a very, very interesting thing to look into. So yeah, in this work, we really focused on some of these simple machine learning as a service platforms, like the one of Amazon that basically just does sort of simple model classes. But yeah, it would be very interesting to see how far you could go with more, I guess, with more complex models, especially neural networks. At some point, the assumption that you know, let's say, the structure of the model or its features might be more difficult to justify. Although if you get services like the ones we've looked into that do deep learning, at some point they might also just give you way more information than you need. And so it's possible that you could still do attacks of this kind. Yeah.
Thank you.
Hi, I was wondering if the lack of confidence would completely break this down. So if you were only given a class label back, or even just some vague notion of the confidence like high, medium, or low confidence in a prediction, if that would totally break this down.
So what I mentioned briefly here at the end was that, so even if you only have class labels, you do have some active learning attacks that can give you good results, not as good, I must say. With lower confidence, so we looked at sort of rounding confidence values down to, say, 2 or 3 digits of precision, and at some point the attacks get less efficient, but you really have to sort of go quite a way into making the confidence values less precise. So I guess at some point you can, well, you can't go further than just giving class labels unless you do something more sophisticated, but at some point, the problem there as well is this tension I was mentioning, is that since these platforms give confidence values, it's probably because developers somewhat want them in their applications. And so, yeah, at some point it's also a trade-off between whether these confidence values are actually needed by an application or not.
Thank you.
Very nice work. And I'm just curious, what if the model contains more than one tree? For example, it's an ensemble of trees or random forests. Can you recover that?
Probably not, yeah. So random forests are one of the model classes that we mentioned in our paper as a potential countermeasure to these type of attacks. Because, I mean, we don't have any formalism for this, but it just seems intuitively very, very difficult to extract a random forest. At least using the kind of techniques we use for decision trees don't seem to apply at all there. So yeah, we didn't find a way to apply these attacks to to random forests. I don't know. Maybe there's a smarter way of doing it, but we didn't think of one.
Right. Thank you.
Hello, sir. Nice work. Have you thought about using this technique to simplify overly complex black box models?
So this is actually what Google's doing. It's something we heard about later after we published this work. So they don't do exactly extraction. They sort of just train a huge neural net and then train a smaller neural net to mimic the input-output behavior of the larger net, but using these confidence values. So instead of trying to learn the class labels, they really try to directly optimize over the probability scores, which they show can actually give very, very good results in compressing models, yeah. So it's a related technique, yeah.
Thank you.
I think this is very interesting work. And I'm interested in this sort of generic model retraining and query learning. But I'm curious what happens when you don't necessarily have the class label and the confidence, but instead you have sort of actions that, so there are cases where there's a model that's I work in privacy a lot. There's a model that's being used, and it's being used to take actions, and those actions are clearly sort of dependent on the class labels and the confidences, but you don't have that, and can you infer the models from those or the training data? And I think that's maybe have you started to work on anything like that or thought about it? Or
so we didn't look at that specifically, so I agree that would probably make it more difficult. However, it seems like actually the way people are meant to use these machine learning platforms is that all this processing of the output would happen client side. So you could think of maybe your mobile app that would make queries to a service and then sort of in the app would convert this to an action or something. So it would seem that, I mean, these machine learning services, they don't provide you with this extra layer, application layer, let's say. So these type of attacks would continue to apply.
good, thanks.
All right, let's thank the speaker again.